Stellar Energy by 6Ledger, period 6. In this slide, we have a picture of color-coded radiation from the sun coming to Earth. Now here we have the radiation measurement of absorption and reflection. The scattering absorption by ozone and other gases is right in this area. Now absorption by CO2, oxygen, and other gases is all in this area right here. Over here we have, the scale right here, 90 degrees north, 60 degrees north, 30 degrees north, and 0 degrees, which is the equator. And then over here, this does not have a label, but this is the month, and this is the amount of radiation it gets. Like, I'm guessing rays or something. Like 600, 500, 400, 300, 200, 100, 0. Now here, hours of day length. The equator, 12 hours of day and 12 hours a night. Oh yeah, and this is the March equinox, June solstice, and September equinox. Now over here we have 10 hours a day, going all the way up to 14 hours a day, and going back down to 12. Now up here, it's, off the scale. I don't know what else to say for this graph besides you can see where each line ends up at each solstice and equinox. Now over here we have the light spectra for HR 799 and the sun. You can see that HR 799 peaks in ultraviolet and goes down in visible and infrared. Over here the sun peaks in visible rays and goes down in infrared. Now, the reason you get a sunburn is because of the ultraviolet rays. Over here, you can get a mild sunburn because of the difference in ultraviolet. Here, you can get a major sunburn because most of it is, it does peak in ultraviolet rays. And over here, there's more visible rays because it's a bigger star. Over here, it's a smaller star, but most of it is invisible because it peaks. Now, over here, most of the visible light is purple and blue. And over here, most of the light is purple and blue because where the peak is in the two colors. A model I used to understand parts in the chapter was pictures of the HR 799 solar system and our solar system. I did not get to finish the picture of our solar system because it would have taken up too much space and you would not have seen most of it. But the reason why I had to do this was because I had to understand the distance from all the objects to the sun and how many objects there were in the solar system. The way I evaluate the statement, it's a cold winter's day, is because I take a picture of Earth's orbit around the sun. The reason why it's usually cold in North America in wintertime is because we're always on a slanted axis. That is a horrible picture of our axis, but who cares? North America is usually over here. The reason why is because we're always on an axis like that. We never rotate our axis like this. When we rotate, we never do that. We're always on a steady axis like that. Always slanted. And when we get over here in wintertime, North America is usually over here. Which means North America is further from the sun than anywhere else. No, this is further, but you know what I mean. So, if we're further from the sun, we get less heat from the sun. The sun gives heat. Oh my god, what did I just do? Okay, let's try that again. The sun gives heat, and we're all the way over here, which means we get less of the heat that the rest of the world gets.